Now, a standard capacitor has a problem. And that problem is that with a standard capacitor, when you have your parallel plates and you've got air or vacuum between those plates, there's a certain limit of electric field that you can get within that plate. There's a certain limit of electric field that you can get between those plates before that capacitor starts to break down. So if the material between the plates of your capacitor is air, an electric field greater than 3 times 10 to the 6 volts per meter can begin to break down the air, and it can cause your capacitor to fail. And in that case, more charge cannot be stored by increasing the voltage across the capacitor. So we saw that the capacitance is equal to Q over V. So the more voltage you add, the more charge you should be able to store on the capacitor, but there's a limit to what you can do with a capacitor that just has parallel plates and air in between. So what you can do is insert something between those plates called a dielectric. A dielectric is an insulating material that you place between the plates of your capacitor, and that automatically can increase the capacitance of your capacitor. And that also allows you to build a greater electric field inside the capacitor, and you can also store more charge, on that capacitor too. Um, Eventually, you'll also reach an electric field within the capacitor where that dielectric begins to break down too, but you can still get to higher electric field strengths inside a capacitor whenever you insert a dielectric. When you insert a dielectric into the capacitor, that increases the capacitance by a factor that we call the dielectric constant. Here it's represented as K. Sometimes I'll write a fancy script K to represent our dielectric constant. It does not have a unit. The capacitance of any capacitor with a dielectric inside it is just the dielectric constant of the material, which you have to look up off of a chart as a property of that material, times epsilon naught times A over D. So how does a dielectric help to increase this electric field that you can get within the capacitor? Well, that dielectric, remember, is an insulating material, and it's going to be polarized by the plates. So here's our parallel plates. We're going to insert our dielectric. Here's our dielectric, and these are the molecules inside the dielectric. The charge on the plates induces a polarization of the molecules inside the dielectric. So we've got our positive plates here, our negative plate here. And so because like charges attract, this positive plate is going to attract all the negative ends of the molecules inside the dielectric. The negative plate is going to attract all the positive ends of the molecule inside the dielectric. This produces a layer of opposite charge on the surface of the dielectric, opposite charge to the charge on the plates. And this also attracts more charge onto the plate because you have this greater amount of charge separation. And then that increases the capacitance because you're able to attract more charge onto the plate. The dielectric constant is the ratio of the electric field in a vacuum to that in the dielectric material. So this dielectric constant has to be determined experimentally. Here's a table that shows the dielectric constant for various materials at essentially room temperature at 20 degrees Celsius here. The second column here shows what's called the dielectric strength. It has units of volts per meter, which is an electric field. This dielectric strength is the maximum electric field strength that's possible inside a dielectric before it starts to break down. Now, let's see. For air, that dielectric field strength is 3 times 10 to the 6 volts per meter. But we see that for all of the materials that are listed here, that dielectric strength is larger, which indicates that you can pack a larger amount of charge, a larger amount of potential difference, and have a greater electric field between those plates whenever you insert a dielectric of a particular material in between those capacitor plates. We're going to work through an example where we have a capacitor and we're going to insert a dielectric into it. In this problem, we're going to insert some paper as our dielectric in between the capacitor plates. This relates very well with the discussion you have for this week, which is to think about how you can create a capacitor out of a chewing gum wrapper. In this problem, we are going to work with a capacitor that has a dielectric inside it. This capacitor has plates of area 2 centimeters by 3 centimeters. That's the length times the width of this plate. And let's see, if we convert that over to meters, that's 0.02 meters times 0.03 meters. That gives us an area of 6 times 10 to the minus 4 meters squared. Okay. And let's see, what else do we know about this capacitor? The plates are separated by 1 millimeter thickness of paper. So the plates here are separated by 1 millimeter, 1 times 10 to the minus 3 meters distance. And we're going to place a piece of paper inside my capacitor as the dielectric. And I'm going to represent my now dielectric that's inside the capacitor here. You take that material and you shove it inside the plates of your capacitor, and that automatically increases the capacitance of your capacitor. Okay, so we've got paper. I'll just remind myself that we've got paper. Now we're going to need to know the dielectric constant of this paper. That's something you can look up in a book. The dielectric constant I'm going to represent as this fancy K, and the dielectric constant for standard paper is 3.7. There are no units on the dielectric constant. And eventually we're also going to need this number, the maximum electric field that is possible inside this capacitor before the capacitor starts to break down. That maximum electric field for paper, it's the maximum electric field that you can get inside this capacitor before the dielectric itself starts to break down. And that maximum electric field is 16 times 10 to the 6 volts per meter. And that's something you'll have to also look up in a chart if required in order to solve this problem, let's say, on an exam or on a workbook problem. Okay, and so then we're asked to find the capacitance of this device. Okay, so we'll write it here. We want the capacitance of this device, and we will also want the maximum charge that we can place on this capacitor with the dielectric of paper inside it. All right, so here's our equations for capacitors and capacitance. The charge on the capacitor is the capacitance times the potential difference. Our capacitance of the capacitor gets increased by a factor of the dielectric constant whenever you stick in a dielectric inside the capacitor. So when you have a dielectric inside the capacitor, the capacitance is now equal to the dielectric constant times the permittivity of free space times the area of the plates all over the distance between those plates. And we still have that the electric field inside the capacitor is the potential difference divided by the distance between those plates. So to get the capacitance of this capacitor, we just use our equation. We just take the dielectric constant, 3.7, times our permittivity of free space, times the area of my plates all over the distance between them. Right, so this is going to equal 3.7 times our permittivity of free space is 8.85 times 10 to the minus 12 coulombs squared over Newton meters squared. and then we have to multiply it times the area of the plates, which we saw was 6 times 10 to the minus 4 meters squared. And then we divide that by the distance between our plates, which was 1 millimeter, 1 times 10 to the minus 3 meters. Okay, so that gives us a capacitance of 1.96 times 10 to the minus 11 farads. So remember, the unit of capacitance is a farad. Where did that unit come from? Well, I've got a meter squared here. It cancels with this meter squared. And I've got a coulomb squared over Newton meter. So the unit is coulomb squared over Newton meter, which is also the same thing as a farad. There are many different ways that you can write the unit of farad, many different equivalent combinations for how you can write that unit, and that's just one of them. So that's part A. Part B, we'll say that. Part B, we've got the maximum charge that we can have on the plates of this capacitor. That maximum charge is equal to our capacitance times the potential difference across the plates. Well, we don't know what the potential difference is across the plates, but we do know from this equation that the electric field is equal to the potential difference over D. We can solve that for the potential difference. So the potential difference between the plates is equal to the electric field times D. So we can also write this as the capacitance, which we just found, times E times D. Now this electric field here, this is going to be the maximum electric field that we can have inside our capacitor before that dielectric material starts to break down. You'll have to look up on a chart, what is the maximum electric field of this paper before it starts to break down? And that would be the maximum electric field that we could put here. That's the maximum electric field that is allowed to exist with that paper in between those plates. And that will limit the amount of charge that we can get on this capacitor. So this is going to equal the capacitance, 1.96 times 10 to the minus 11 farads, times our electric field, maximum electric field we can have with the paper, which is 16 times 10 to the 6 volts per meter. And then we just multiply it by the spacing between our plates, which was 1 times 10 to the minus 3 meters. All right, so that gives us a charge on the plates that we can get of 3.14 times 10 to the minus 7 coulombs. I'm going to write this in microcoulombs. So we've got a conversion factor that in 1 coulomb, there's 10 to the 6 microcoulomb. You can multiply this number by 10 to the 6, and then this gives us 0.314 microcoulomb is the charge that we could have on the plates of our capacitor. Positive 0.314 microcoulombs on the positive plate, negative 0.314 microcoulombs on the negative plate.